In this video, I want to have a look at induction proofs that involve sums. So before we do this, we need to introduce something called sigma notation. So sigma notation is a concise way of writing sums. So we've got two examples here. The reason it's called sigma notation is because of this symbol here that looks kind of like a capital E, and that's the Greek letter sigma. So what it means if we've got n equals 1 and a 5 on the top and we want the sum of n squared, what that means is we're going to substitute in every number from 1 to 5 into here and add them all together. So for example, we'd have 1 squared and then the next number, so we'd have plus 2 squared, plus 3 squared, all the way up to 5. So it's a much shorter way of writing this whole thing out, and you can imagine it's much easier, especially if we had a lot more terms. Or it's also another way of writing it if we have an infinite number of terms and we can't write out the sum in full. So that one would simplify down to 55. Another example we've got here from n equals 3 to 6 of 5n minus 2. So we'd sub in each one again. So we'd have 5 times 3 minus 2 plus 5 times 4 minus 2 plus 5 times 5 minus 2 plus 5 times 6 minus 2. And we could work all of that out to be 82. All right, so we can use this sigma notation as well in induction proofs. So we're going to have a look at an example of that. All right, so our example asks us to prove that the sum from 1 to n of 1 over 2r plus 1 to r minus 1 is equal to n over 2n plus 1. So we're going to start the same as we always do. We're going to show that this is true for our smallest value, which in this case is going to be 1. So to make this a little bit easier, I'm actually going to rewrite this whole thing out as its sum. So this whole thing on the left-hand side is going to be equal to 1 over. Now if I substituted in my first value, so I'd substitute in 1, I'd have 2 plus 1, so I'd have 3. And then I'd have 2 minus 1, which would be 1, so I'd just have 1 over 3. Just make that a little bit shorter. My second term, I'd sub in 2, so I'd have 1 over, and I'd have 5, and then 3, so I'd have 1 over 15. And I could keep going all the way up until I got to 1 over 2 to the capital N, because capital N is my upper limit, plus 1, 2n minus 1. And I want to prove that that is always going to be equal to n over 2n plus 1. So I've rewritten my question rather than using this sigma notation. I've rewritten that whole thing, and this is now what I'm going to use in my proofs. So if I had that my capital N was equal to 1, then that means I'm only going to be looking at this first term. So that means that the right-hand side of my equation is just going to be a third. And the that's my left-hand side is going to be equal to a third because it's just my first term. My right-hand side of that equation, so this one, I'd end up with 1 over, and I have 2 times 1 plus 1, which is just 1/3. So because my left-hand side is equal to my right-hand side, then I can say therefore true for n is equal to 1. So I'm going to assume that this is true for n equals k. So that means that we're going to assume that 1/3 plus 1 over 15 plus all the way up until we have 1 over 2k plus 1, 2k minus 1. We're going to assume that that's equal to k over 2k plus 1. So once we've assumed that, we're going to prove that if that's true, then it's also going to be true for n equals k plus 1. So that means that we're going to have 1/3 plus 1 over 15 plus all the way up until I have 1 over 2 k plus 1 to k plus 1 minus 1. And I want that to be equal to k plus 1 over 2 k plus 1 plus 1. Now I'm going to simplify that a little bit before I break it into right-hand side and left-hand side. So I'm going to have a third plus 1 over 15 plus all the way up. And if I simplify this term, I'd have 2k plus 2 plus 1, so 2k plus 3. And I'd have 2k plus 2 minus 1, so 2k plus 1. And I want that to equal to k plus 1 over, again, if I expand that one out, I'd have 2k plus 3. So this is what I'm trying to prove. So I'm going to take my left-hand side, and to make myself have a little bit more room, I'm just going to get rid of all this stuff for a minute. All right, so that means that the left-hand side of that equation, so this whole thing, I'm going to write it out, but I'm also going to put in the term before this. So if this is my k plus 1th term, then the term before it would have been my kth term, which was this guy here. So I'm going to write it out as a third plus 1 over 15 plus dot, 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 plus my kth term, which was 1 over 2k plus 1, 2k minus 1, plus 1 over, so this whole big thing here. So we had 2k plus 3, 2k plus 1. So that's the left-hand side. Now I know that this whole chunk here is going to be equal to this because we've assumed that that is true. So I'm going to replace that with my k over 2k plus 1. And then I've still got this term on the end as well. So I'm going to have plus 1 over 2k plus 3, 2k plus 1. And just to show my understanding of where this has come from and why I can replace it, I'm just going to write from assumption. Or you could write using assumption. It's up to you how you phrase that. Now I've got these two fractions I want to add together, which means I need them to have a common denominator. They already both have a 2k plus 1 there, but this one also needs a 2k plus 3. So that means I'm going to multiply top and bottom of this fraction by 2k plus 3 to make them have a common denominator. So that's the new numerator of this one, and I've also got my plus 1 on here, and that's going to have the common denominator of 2k plus 3, 2k plus 1. Now if I expand that out, that's going to give me 2k squared plus 3k plus 1 over 2k plus 3, 2k plus 1. Now I'm going to factorise that quadratic that's on the top. You can use whichever method you like to factorise that. So I'm going to have 2k and k, 1 and 1, and to get that 3k in the middle, they're both going to have to be positive. And then you can see that the numerator and the denominator both have that 2k plus 1. So those will cancel out, and I'll just end up with k plus 1 over 2k plus 3. And that is exactly what we were looking for. So that's equal to, I'm running out of room down the bottom there, that's equal to the right-hand side. So then we need our conclusion. So we can write therefore true by induction for all n where n was greater than or equal to 1. So that's having a look at induction where it involves sigma notation.